All right, finally I've got everything set up. Gotta make sure my daughter does not take my iPad anymore. Like, she has set everything to be different. Okay, well, we'll manage. All right, let's get started. Sorry for the late start today. So today we're going to be, let's put it this way. We're going to be talking about something that is very real. And it kind of permeates a lot of what we do in the ML world, in the high performance computing world. It's a reality that, I think when I first learned about this, again, when I was in your shoes, I thought, I don't really need to worry about it. I'm going to focus on the regular stuff because it's interesting. I get it. Makes sense. It's beautiful. This is ugly. And, well, we'll only worry about it when we're actually building something real. And it turns out that dealing with, what I'm particularly talking about is this notion of sparsity. Okay? And it turns out that the real world is so sparse that if we don't think about it from day one, anything we're going to try to build is going to be garbage. It's just kind of an abstract academic exercise. Okay? So we have to pay attention to sparsity. And today, I think I'm going to introduce the concept to you, give you some ideas to kind of put in your mind about sparsity. We'll talk about sparsity again on Tuesday because it's just such a big topic. And you'll do a lab assignment on it, okay? But we're just kind of scratching the surface. We're going to present to you about 3 or 4 different ideas involving sparse methods, but the world is full of different ideas. In fact, you may come up with ideas as we go through today's lecture about how to do things differently. Okay. So that's what we're going to talk about, and for many of you, it will be very new. Okay. But before we go there, any questions, comments, feedback that we should talk about? No? Okay, well, let's get on with it then. Now, like I said, we can think about a matrix multiply as I've got n by m, x by y data in matrix M, matrix A, then I'm multiplying it by matrix B, and both of these systems have lots of data in them. In fact, when we think about an image as a matrix, yeah, every pixel has some value in it. And we could think about the image as a big matrix, but it's often the case, in fact, almost always the case, that these matrices don't have data at every point. Okay, and that's the basis of what we call a sparse system. And typically what we want to do on these sparse systems is not just matrix multiply, but something more complex, like solving a linear system around them. I've got a bunch of unknowns, I know a bunch of constraints, I want to estimate what those unknowns are. And we're going to use techniques that are very sophisticated, like some kind of iterative technique, like an iterative conjugate gradient solver, that's over time trying to estimate what that solution would look like. We don't have to worry about that here. But all I want to impress on you is we start with a sparse system, Matrix multiply is or matrix vector multiply is a primary operator. And with that primary operator, we're going to do something much more complex, like solving a system of linear equations using an iterative technique. So it's not just we're going to do one matrix vector multiply in a sparse system. We're going to do many, many, many on very large systems. Okay? And that's what's happening when we process data. All right. Now, let me impress upon you a different perspective. There are also systems, by the way, my previous slide was really kind of referring to a numerical technique. Like, for example, if you're trying to build a system solver for fluid dynamics, maybe that's what you're doing. Or some kind of engineering process, that's what you're doing. Circuit simulation, that's what you're doing. But with this new, brave new world of AI, we also see sparse systems. I'll give you a few examples. You know, let's take Netflix, the recommender system in Netflix. Right? We all know what it is, or the recommender system in Amazon. We all know what it is. But let's think about it for the moment. Okay, what we have is, we have a bunch of users, you and me, and we have a bunch of content. We have a lot of content and we have a lot of users. And it is very much the fact that any one user has only sampled the content space very, very sparsely. Right? I mean, yeah, no matter how much of a binge watcher you are, there's no way you're going to watch all the content on Netflix. In fact, the average user probably far less than 1% of all the content. Right? So this system, lots of users, 1% of the content viewed, well, that's a sparse system. Right? And the same thing is true with something like Amazon or Apple Music or any other system where at the end of it, what we might be wanting to do is to make some kind of recommendation. So how do we deal with that, right? In fact, that's a lot of users and a lot of content. So that system will never, ever be represented like the matrix that we represented in our matrix multiply kernel. There's no way we could. But at the end of it, one way to do these recommender systems is to use an idea from linear algebra called matrix factorization, which again uses this notion of matrix multiply. So again, we're going to apply linear algebra in some sense to do the recommender system. So how do we represent this very sparse system and then do these linear algebraic operators on them? That's what we're going to talk about. Okay. Make sense? Pretty intuitive, right? And it turns out we can spend a day just talking about various examples here of systems that are very, very sparse. Okay. Question? No, in fact, that's part of the art. And we'll see that next lecture. Not only are they sparse, but they have patterns to them. Okay, what we'll talk about is in certain engineering systems, matrices may be banded, meaning there may be a band of non-zeros. Or they may be triangular, meaning, well, the upper quadrant, the upper triangle is all zeros. And the lower triangle has some non-zeros. Or they may be just very random. Like, for example, the Netflix matrix, right? Or there may be, I wouldn't call it random. It's not random, but the patterns are not like visible to us, right? We have to do something to the data in order for it to be visible to us. It's all part of the art. Okay. There's no one technique that will solve sparse systems, because at the end of the day, your sparse system may be very different than my sparse system. And the optimizations we would do will be different. Okay, I'll give you an example. So one of the projects, actually this is one of my alchemy projects. It was the team started in alchemy. We were building a search engine for private platforms using NLP, natural language processing. The company morphed a bit, and we started to develop a recommender system for a manufacturing company, let's call it that. Fortune 500, very big, lots of parts that they're trying to recommend to their customers. Okay, it's just like the Netflix thing, right? That's what a recommender system is. Got a bunch of things, got a bunch of users. Which of these things will that one user most likely buy? So we built the system for them, and we were using AI techniques, built a deep neural network to do it. And what I want to show you here is the weight matrix for that deep neural network for a production recommender system. You'll never see this. Right? These are the crown jewels of Amazon. They'll never show this to anyone, or for Apple Music, or for whatever. But this is a small slice of the weight matrix for this company that we built the recommender system for, on real data, trained on real data, millions, hundreds of millions of data points. So what I'm trying to impress on you is, if you look at the coefficient matrix, which is here, and kind of the coefficient color scheme, green is 0. Dark blue is more negative, and yellow is more positive. Most of this thing is 0. In fact, there's a huge band right here that is almost all 0. Okay, and these are the weights from a trained deep neural network. Most of the information is here and within the structures over here. Okay, this is not the full weight matrix, but it's a big part of it. And it's like 30,000 some odd weights, most of which are 0. Okay, so again, when we're going to do anything with this, we've got to take those zeros into account. Okay, and again, just to share some statistics with you, the Netflix data set. By the way, if you're interested in the history of recommender systems, and recommender systems, by the way, are, I would say, one of the big success stories in terms of AI and deep neural networks. You should understand the Netflix challenge. It's worth kind of reading up on that history. Kind of started, I think, 2000 timeframe, 2000, maybe mid-2000s, 2005. I don't remember the dates. But it was a challenge, kind of thrown out to the community. The academic, the data community, anybody. Kind of Kaggle, if you're familiar with Kaggle, before Kaggle. Okay. This was probably the first Kaggle type thing. And so basically the challenge was, here's our data. Here is the matrix. Again, very sparse. Users and their ratings of all this content. And we can recommend at an accuracy of this, we being Netflix. Whoever can beat this after 1 year of work on it, wins $1 million prize. That was the Netflix challenge. And I think it just created such an intense amount of effort within certain groups of people that breakthroughs were made in this space. It's a fascinating story that ultimately, I think, contributed to the growth of AI. Because, you know, the deep neural network community started in 2012, which was after the Netflix challenge. But kind of all of that contributed to this, to effectively bring us where we are right now. The growth of recommender systems really came out of that Netflix challenge. So yeah, that's Netflix, and their data set is about 1% sparse, meaning only 1% of the elements actually have a rating in them or a non-zero in them. And then the Amazon data set, right, you can kind of understand lots of users, let's say 300 million users, with lots of products, 160 million products. That's incredibly sparse. And yet, they're effectively able to make recommendations. Right? Whether you like your recommendations or not, they actually work for Amazon. Okay, any questions about this? Okay, one more kind of motivation around this to kind of switch it a bit, going back to high-performance computing world. So instead of AI, let's turn our attention now to things where we're using traditional techniques to solve big problems, whether it's with climate prediction, atmospheric prediction, cosmology, relativity, molecular dynamics, quantum physics, da-da-da-da-da-da. Right? This is, scientists are using computing, to no surprise to anyone in this room. And the general category of what they do is called high-performance computing. And over the years, people have tried to kind of boil everything down into a few kind of exemplars of things they do. You know, these are the codes that we try to optimize. Can't say that I'm familiar with many of them, but there are plenty of people on campus even that are the experts here. This is scientific computing. And what we can do is kind of take all these problems and talk about what internally they're doing. You know, are they using grids? Are they doing dense matrix? Are they doing sparse methods? Clearly, if you look at this on the types of algorithms they use, sparse techniques are very important. I think this probably underestimates really the importance of sparse techniques. Okay, and I would imagine that some of you are working in these realms, right? Oftentimes, when I teach ECE 408, there are people from chemistry or physics or astronomy in the class. But this is what they do. Okay, clearly GPU computing is a strong part of the high-performance computing world. Okay, any questions about the motivation here? Good. Let's talk about the nitty-gritty. Okay, so hard example. What is it that we're trying to do? Let's boil it down to this, because once we put the framework together for this, everything falls out from it. Okay, everything can be done once we solve this. So let's say our particular problem is we're trying to do a matrix vector multiply. A times X equals Y. Very simple, right? And we know how to do this from an algebraic perspective. But what we're going to say is A itself is sparse. Maybe it's 1% sparse. meaning 1% of the elements have actual data. The rest of them are zeros. Okay, so then we end up with issues of, well, yeah, we want to be able to calculate this, but we do not want to store A explicitly, meaning there's no point in storing those zeros, right? Because it's mostly zeros. And not only is it mostly zeros, but it's huge, right? Maybe it's 1,000 by 1,000 system. That's 1,000,000 elements, most of which are zero. And I would say 1,000 by 1,000 is small. What if it's 10,000 by 10,000, right? Then we run into issues with even storing it. So we've got to squeeze out those zeros. Okay. Now at this point, everything I'm going to tell you, you could derive on your own, right? This kind of optimization is a problem. Given your background, you should be able to say, yep, I'm going to try it this way. So whatever I'm going to show you should be derivable by you, I would expect. Okay. And like I said before, there's dozens of techniques here. And which one we use, which one applies, depends on the sparsity. Okay. So let's talk about the first variation here. Okay. And again, we're going to set the context. And the context is going to be, we're doing sparse matrix vector multiply, SPMV, sometimes we'll call it that, where you'll have a number of threads where each thread is calculating one element of Y. That is, each thread is reading one row of A. So thread 0 reads row 0 and computes the dot product with vector X. Thread 1 reads row 1, dot product with vector X, and so on and so forth. Okay, so that's the context. We will first talk about the CSR format, probably the most elementary of the formats for representing a sparse system. Okay, and what we're going to do is we're going to say, well, at the end of the day, I could represent this as a two-dimensional matrix explicitly, but then I got to store the zeros. I need to be able to recreate this at the end of the day. But I'm not going to store the two-dimensional matrix. I'm going to store three things instead. First thing is the data, the non-zero data. So I'll take all the zeros out. There's only 7 non-zeros in this 4x4 matrix. 3, 1, 2, 4, 1, 1, 1. And that's what I store in the array data. Okay, so those are the non-zeros. Ultimately, what I need to do is I need to be able to recreate this and compute as if it were a dense matrix, right? Thread 0 needs to know how to get the 3 and the 0 and the 1 and the 0 so we can calculate the vector multiply, the dot product. Okay, so we store the data, and what we're going to store explicitly is the column index for each of those data. So we've got 7 data, and we're going to store 7 indices. Okay? So this 3 is in column 0. So column index 0 is 0. That corresponds to the 3. Column index 1 will correspond to this. Its column is 0, 1, 2. Therefore, there's a 2 there. Column index is a 0. Is a 1. Therefore, there's a 1 there. Column index is a 2. therefore there's a 2 there. Column index is a 3, therefore there's a 3 there, and so on and so forth. Right? So the column index is really the y-coordinate we can think of for the data. Okay, what we need is the x-coordinate. So the way we're going to store the x-coordinate in the CSR format, the compressed sparse row format, is via pointers instead. So what the row pointers, and there's 5 of them in this case, tell us is the start and stop for all the rows. We've got 4 rows, so I need to know where this one starts and where this one stops, where this one starts and this one stops, and so on and so forth. Okay, row 0 starts here and ends here. That is, it starts at the element 3 and ends at the element 1. Okay? So what we'll store is, this is index 0, that's the start. And this is index 1 in data. But we'll actually store a 2. Meaning it ends at the second element. Do not include the second element, the third element, I guess. But index 2 is the end. So the 0 and the 2 correspond to the start and the end of row 0. And again, we're storing the end plus 1. Okay. So the start and the end of row 1 are the 2 and the 2. Meaning row 1 starts at element 2 and ends at element 2, meaning it's 0. There's nothing there. It's an empty row. It's all zeros. The start and the end of row 2 is element 2, but ends before element 5. So coming back up to data, right, what that tells us is row 2 starts at 0, 1, 2 here, and ends at 0, 1, 2, 3, 4 here. We're not going to include the 1 because, again, we're going 1 beyond. Okay. Let me show you what this looks like from the perspective of the data. Okay, so here is the data. Here is the column index. Hopefully that's very clear to you. And what the row pointer tells us is where in the data do the various rows start and stop. Any questions on this? Yes?
Do we also need to store the matrix?
I don't think you need to, but you could. It depends on the calculation that you're performing at the end of the day. Okay. Again, like if this is confusing to you, let's look at the next slide. Well, not this slide, maybe the next one after this. Question? No, we never want to store the matrix explicitly. Okay, so probably when the data is even generated. Okay, nowhere in time is that full matrix ever stored in memory. Think about it that way, right? Because if it did, we would need terabytes of zeros, and no one wants to spend the time to do that, right? Okay, think about it from the Netflix perspective. I rate some content, so it's me putting one element into an X and a Y, right? That's all we need to store. Make sense? Okay, good. All right, so again, coming back to our example, what we have is, ultimately we have a bunch of these threads, like we've got the red thread, or the top thread reading the red row, calculating the red element of y. Okay, so that thread needs to be able to figure out which three elements it needs to multiply together with the x vector, right, in order to do the dot product. Likewise, the second thread needs to read the blue row, or whatever thread that is, needs to read the blue row, and so on and so forth, in order for each thread to calculate the appropriate output element in y. So here's what that code would look like. And hopefully this will kind of crystallize it for you. Okay, first let's start with the input parameters. I need to know the number of rows. I need a pointer to data, to the column index, to the row pointer. I need to know x, which x can be dense, right? X can be a vector. It's just a vector. It's very likely to be a dense vector. But I need a pointer to it. And then I need a pointer to the output. So line 2, let's figure out our index. So I got to calculate which output element I'm calculating. Standard block index x times the dimension plus the thread index. It's just calculating, am I generating output 0, output 1, output 2, etc. So I take my row number and make sure it's in the number of rows, right, so that I'm not out of bounds. And then I set up to do the dot product. Okay. Row start is row pointer, row. It's telling me the starting point for my row vector in the matrix A. Row end is row pointer plus 1. Right? It's the next element, and it's telling me when I should stop. So then I've got the for loop here. I start at the start, and I keep going until I reach row end, all the while incrementing, and then I calculate the dot product, which is data element times column index of the element. Why do we need to do column index of element? What is that accomplishing? Yeah.
Because the transpose to turn it indexing into x columns of
Close. Yeah, I think you're on the right concept, but I want to hear it slightly different. Yeah, do you have a question?
Okay. So
Go ahead.
what if the start and row end are themselves sparse? You're iterating from row start to row end, right?
Yes.
Your matrix is like really long.
Yes.
And only a few elements in the middle between row start and row end are actually like not.
No, they are all non-zero by definition. What you're saying is, why would I ever put a 0 into data?
No, you wouldn't. But like when you're okay, those are already non-zeros.
Yeah, keep in mind that row start and row end are essentially pointers into data. Data's right here.
Oh, and you don't care which column index that is because you're.
Yes. So coming back to your point here, right, I asked why do we need to index into X using column index? Because, okay, I've got this 3, I've got this 1 that are part of the first row. This is at column, I don't remember now. Well, let me show you the matrix. Here's the original matrix. So 3 is at column 0, 1 is at column 2, right, in row 0. So when we do the dot product thread 0 for thread 0, we want to take the 3 and multiply it by x0. We want to take the 1 and multiply it by x2, right? How these elements are spread into x is defined by the column index. So therefore, when we look at the code itself, we're going to use column index to find the right element in x in which to multiply the data. Okay. There we go. Took the CSR format, which, you know, intuitively, right, like I said, all of you should be able to derive that and convert it into CUDA code. Any questions on this? Yes?
For the second iteration, what?
Okay, let's back up. Let's make sure we address your question precisely. Okay, so you're saying on the second iteration, right, of thread 0. Okay, so thread 0, iteration 1, let's just walk through iteration 1. Let me see if I can write with my finger here. So iteration 1, what is row start? Actually, what is element in iteration 1? Element will be 0. Yeah? So we're reading this 3 in iteration, in the first iteration. And so this is 0. What is column index 0? Well, that's also a 0. So what we end up reading is x 0 for that first pass through the loop, right? That makes sense? Everybody on the same page? So we're taking this 3, which is what we get with data 0, and multiplying it by x0, which is correct. That's what we want to do. Now let's come back through and do the second iteration. What does element equal now? Well, element is 1, right? We just incremented it. What is column index at element? Column index at element is now 2. So what we're going to do is we're going to multiply it by x2 in this case. What are we multiplying by x2? Data element 1. This. Right? Which is exactly what we want to do. We skipped over the 0 that was in between the 3 and the 1 in the original matrix. Make sense? Does that answer your question? Yeah? Yes?
We're looking at data that's encoded where zeros are essentially values that we don't want to look at, but is there a way to do this where, say for example, 0 is the quantity we're trying to analyze?
Boy, that would make things really tough. Right? Because that's what that's saying is, well, you can't ignore the zeros, you need to explicitly store them. But if that were the case, simple fix, right? As long as we don't have to explicitly store them, right? What we can do is modify this inner loop to do something with the zeros, right? That's not that hard. We don't have to store them. That's the key. Couple of questions, yes?
So for each thread, the amount of work is kind of different.
Oh, yes.
So wouldn't that leave a lot of thread idling?
Yes, 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 yes. Here we go. Because what you're talking about is the slippery slope. Right? This works, but it's not very good. Let's make it better. Okay. We'll get there, yeah.
Would it be worth storing X in shared memory? Because since we're doing sparse accesses to the
Again, that's all part of the slippery slope, right? We convince ourselves that this works, and it does, and now we want to make it better. So how do we make it better? Well, good. That's a great question. One of the things, as you point out, right, there's just, all the threads are doing different amounts of work. That's never a good situation for an architecture like a GPU. Lots of load imbalance and lots of irregularities. So can we fix that? And the other part of it is, well, all the memory accesses are uncoalesced. So if we're reading from global memory, thread 0, iteration 1 is reading 3. Thread 1 is reading nothing, actually. Thread 2 is reading the 2, and thread 3 is reading this, and da-da-da-da-da. Right? It's all sparse. And for a large system, that could be very, very uncoalesced. So threads doing a different amount of work. They're all uncoalesced. Let's see if we can do something about that. So that brings up a format called the LPAC format, or the L format it's often called. And this was developed long before GPUs, because the particular problems I talk about here affect all kinds of parallel high-performance systems. Right? The idea is really simple. What we'll do is, we will insert some number of zeros. I mean, yeah, we could put a 0 there, right? Putting a 0 doesn't hurt anything. It takes up space, but doesn't hurt anything. So we'll store some amount of zeros, but far fewer zeros than we would if we were storing the thing explicitly. And then second of all, we will transpose it. Okay, so instead of storing it in row major order, we'll store it in column major order. And by doing both things together, we'll address the deficiencies we just talked about. Okay. Here, now things start to have some balance to them, which actually will help for subsequent optimizations we perform. Okay, so now what the threads will do is they will read the columns of A as opposed to the rows of A, because we're going to store them in column order now. And then dot them with the column vector X. Same computation, but we're just storing things differently. Okay. So let's take a look at what this looks like now. The padding doesn't change anything. Right? It just means that, well, okay, fine, we're going to store in data, we're going to store some zeros just to pad things out. Column index, actually, no, I take it back. Now, because we've padded everything, we we don't need to store the row pointers explicitly because they're implicit, because we know where all the rows start and stop, right? So we don't need to store the row pointers. We know that if I'm operating on row, I know where to start the row, and I know where to end the row, because each row has num elements in it, a fixed number of elements. I don't need to store row pointers anymore. That is, if all the rows are the same size, okay, which is what I'm assuming in this code. And now, because we've transposed everything, what we have to do is change the way we're indexing into data and the way we're indexing into column index correspondingly, because everything is transposed. Okay. But otherwise, the computation looks pretty much the same. That simple change substantially improves the performance of things like the SPMV kernel. Okay. Any questions on this?
But if there's a line that, but if there's a row, end up storing almost the entire.
See, I love this. We're all anticipating where the things break down, right? So his point is, hey, wait a minute. What you did was you made everything the same size. Coming back here, right? What I did was I added enough padding such that everything had the same number of elements in each row before I transposed it. But if I had one row that had lots of non-zeros compared to other rows that have all non-zeros, let's say, then I end up padding everything, and I may end up creating a matrix that's not substantially smaller than the explicit one, right? Yes, that's a problem with the L format. So if I have that situation, what do I do? We'll come to that, okay? We'll come to that. But let's address the memory coalescing thing for the moment, okay? So here are my threads. Thread 1, 2, 3, 0, 1, 2, 3. And what I'm doing is I'm storing the rows in the original A as columns. So what that means is when we start the kernel, what I'm really going to access in that first iteration is 3, pad, 2, 1, which is great. That's exactly what I want, right? Because now, at that particular point in time, all these memory addresses are coalesced to a single burst. Right? I'm making much more effective use of my memory bandwidth at that point. And then so on and so forth. Right? So this thing here, this transposition, is pretty effective. And we're going to see that again a couple of times. Okay. Any questions about the L format? Okay, good. But we still have this issue, right, that he brought up, which is, what if one of my rows is very, very long? Before I talk about the solution to that, let's talk about yet another format. This one is intuitive, super intuitive. It's called the COO format, or the coordinate format. Okay, and what we're going to store is the data. Right? Again, I just store all the non-zeros. I will store a column index, like we were doing previously, but I will also store an explicit row index. So what I have is the data and the x and y coordinate. The data and the x and y coordinate. Data, dot, 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 dot. Very intuitive. In fact, it's so cool, this format, that I can reorder the data in any order I want. Right? Because I know where it belongs. as long as the threads can find them. Make sense? Okay, so now if we were to operate on this, a couple of things kind of emerge. We unlock an amount of parallelism here, right? Because now, does it really matter which row a thread is operating on? Because as long as I grab some data, I know what to multiply it to, right? I know that, okay, this is element, the data is 2, it belongs to column index 1, row 2, I know which x to go and find to multiply it with, right? It's going to be x2. And I know where to add it to. I know where to add it to y2. So now a thread can operate on any of this data. I just give it a bunch of data, but I need to do one thing in order for it to all come together. So 2 of you are seeing it, right? Let me walk through that algorithm one more time. I've got a bunch of values. I've got a bunch of threads. And my approach is, well, okay, thread 0, you take these. Thread 1, you take these. Thread 2, you take these. And so on and so forth. My algorithm is, okay, I know the data. I know which x to multiply by. I know which y to add into. Just loop until you're done. Yeah.
But then you're dealing with
Very specific. What synchronization issues? Raise your hand. Yes.
So the output matrix as dynamic. Was you have 2 threads that are trying to write the same location. You're going
Atomic add, because now I have 2 threads potentially adding at the same time. Right? It's our histogram problem all over again, except we're not incrementing the histogram, we're adding a value to that histogram. Right? So when we think about this, here's the code. The code is remarkably easy. Well, I mean, I've removed all the other lines, but that's the code. Problem is, I have to protect that update to y with an atomic. Right, because, as I said, I've got all these threads operating on data. They're reading, and they may end up writing to the same location at the same time, and therefore I got to synchronize. Specifically, synchronize with an atomic operation. Okay, make sense? Question.
Wouldn't this also be slow?
Yeah, so unless we can figure out a way to privatize and update in shared memory, it becomes complex. Yeah.
let's say we try to update in shared memory as buffer, like when you do the increment. You're multiplying 1 row with 1 column at a time. You want to optimize so that you finish all like the partial dot product sums and update to that shared memory location before you move on.
Yeah. I mean, so all of this has to be done, right, in order for this technique to be effective. By the way, all of this is costly. So it's an intuitive representation, but it may not be the best representation. Okay, yes.
although those are good techniques, would it be cheaper to do that or to, before we our data so that we minimize our?
That's hard to do, right? We'd have to analyze the data pretty carefully to know what the minimization on those collisions are, right? By the way, minimizing the collisions doesn't help us because either we have to include the atomic add or we remove it, right? The atomic add is always going to be costly, collisions or not. Yes? Yes, and why? Why is that? Yeah, in fact, so your point is good, right? That we never really talked about space complexity for these techniques as we compare them, but that's one of the things. CSR, I have to store the same data. CSR versus COO, store the same data, no difference. Store the same column index, no difference. What's the difference between row index and row pointer? That's what you're getting at, right? Yeah. Well, what is the difference, right? Will one require more space than the other? And what are the influences on that? Yeah.
So with row pointers, essentially all you have to do is for each row, you have to only store 2 values. But if you have the row indices, then for each element in each row, you have to store 2 values. So you end up with, at best, if you had one element, it would be the same amount of storage. But for each, nth additional element, then you have to add 2 additional, bytes or integers, whatever you're using for that element. So it's much larger overall.
Good, right? So it comes back to the statistics of the data, right? If I have many elements per row, but still far fewer than the full number of elements, well, then COO starts to become a little more expensive than CSR, right? Yeah.
Is there any computational benefit to storing the row pointer, like bursting or some stuff like that, or it's just that it saves space?
It's hard for me to answer that absolutely, right? Because it depends on so many factors. There may be a benefit. I don't know. I don't think there's a first order benefit. Okay, now, we talked about CSR, we talked about the LPAC format, L format, and COO, all right? Sometimes the best approaches are hybrid approaches. Again, because the amount of computation and memory requirements are so intensive for these important workloads, we're going to try to apply the best solution we can. This is my point at the beginning of the lecture, right? My mind likes simplicity and beauty. And I thought, well, hybrid things like this are ugly and very specific to implementation. I thought, I wish I didn't have that perspective back then, because I think the beauty is really how to get it to work and work well. So here's an example of a hybrid. We take the best of L, which is coming to his point. He made a very good point when we were talking about L. He said, what is the situation where we have one row that has a lot of elements, right? So what we're going to do is we're going to say, well, let's pick a threshold. And I've got all these orange boxes here that are non-zero. Let's represent most of them with the L format. We kind of create a regularized structure that is mostly dense with some padding. And then for these oddball outliers, blue ones, let's store those in COO format. So the issues with COO format are, well, yeah, it's nice, it's conceptual, but man, we've got that atomic, and that's going to burn up some efficiency. Well, at least we've minimized it, right? It turns out that these kinds of things, like if you look at the CUDA libraries that do sparse linear algebra, they use things like this because they work very well in practice. Okay. So in this case, coming back to our particular example, what we're going to do is we're going to pad. Oh, by the way, right, we're going to use L format, not CSR format, so everything is transposed. And what we're going to say is we're storing the data in L format such that each row has 2 elements in the L format. And we've got row 1, which originally had all zeros, we'll just store as padding. Okay. And we had one outlier, which we're going to store in COO format. That is data 1, index, column index 3, row index 2. So we end up reducing the amount of padding. Everything looks good. Now, it may be that this particular piece right here, we could execute that on the CPU instead of on the GPU to kind of finish off the process, right? All that is possible. Okay, any questions on this? Yeah, question back there.
So in terms of like,
Yeah, exactly. Exactly that. Yeah, exactly that. And whether it's 10% or 5% or 15% depends on what. I mean, there's no wrong answer, right? Your code will work. It just may not be the most efficient answer, right? It's a question of efficiency. Good. Yes.
so we're basically storing one matrix into 2 different. In reality, we would like to store all the data in one place, like in one database. But before we do the multiplication, we
Well, very good question. I like this question. So he's saying, hey, you drew all this up on the slide, but how does it work in practice? Well, imagine, okay, let's build a parser. So I have the dense system, okay, and I need to convert it into this hybrid system. So I first pick a threshold. Maybe I analyze the full system somehow, and I say, well, I'm going to put 5% of my data into this COO format. Or my rows will be no more than n elements. Anything longer than n elements ends up in COO format. So then what I do is I run through my data and I build this, which is I'm going to create a data array, a index array, and a pointer array that correspond to the L format of this. Okay. Not all of my data will fit into it. There will be some piece of my data that doesn't fit here that I will need to represent in this format. Okay. And for that data, I need this array data, which is different than that data, right? Let's call this data underscore COO. And then I need a column index and a row index for each of those. So my original data, whatever form it was in, now is represented by 2 data structures. First data structure has these arrays. The second data structure has these arrays. My CUDA kernel might have 2 parts. Actually, maybe it's 2 CUDA kernels. CUDA kernel A, go and do the matrix vector multiply with this data structure. I don't have a complete answer yet because I still need to Then run the second CUDA kernel to factor these elements into the data. And then we're done. Make sense? In my example, I parsed it before, okay? But once it's parsed, it's always two things, right? It's the regular structure and then all the leftovers, right? It's not one pointer, but now it's 6 pointers into the data. Make sense? Right? Originally, when we were representing A, I just needed one pointer, point to A. Now, I no longer have one pointer pointing to A. I've got 6 pointers that represent all these various pieces of information. We would need 2 kernels to do this, right? We need one kernel to process the L part, and then another kernel to process the COO part. Or it could be that we have one kernel to do the L part, and then we just use the CPU to do the COO part, right? That's also possible. Make sense? Okay. Well, good. Yeah, question? Yeah, like I said, there's an endless supply of ideas here on how to make things more efficient, depending on the specific sparsity of your system, right? Let me kind of put this into context, right? There was this slide. I showed you at the beginning, right? We kind of think about computing the wrong way sometimes. Right here. Sometimes we think about computing as like, I'm going to launch my code, and I'm going to sit here until it's done, and I'm really annoyed if it takes longer than a couple of seconds, so I want to speed it up. Yeah, that's from your and my perspective. Maybe that's the way computing works, but let me put things in the context of somebody doing any of these. Okay, so for any of these, the code is going to take forever to run. Not hours, not days, but if we don't do anything, it will take years to get the computation out that we want, right? It's just so complex. Second, the National Science Foundation and the government will spend close to $1 billion building me a system to solve this problem. It's that important. It's true for many of these things. Okay. I remember when I was a student, oftentimes, the question would turn into this, that, hey, we could start working on this problem today. Let's pick, a problem in quantum chemistry. It's going to take 10 years to get the result on this computer that's right here. Okay? And in 10 years, we'll have the answer. And we'll all be happy because we got the answer. Or we could wait 9 years, and Moore's Law will have scaled computers up to the point where, 9 years from now, the computer that will be around will solve it in a week. I mean, this sounds weird, but that's actually what the truth was. May not be the truth now, because I don't know that Moore's Law is still progressing that way. What's the point? The point is, these problems are specific. The computation patterns are known. We still cannot solve them because the data and the system size and the amount of computing required is just so immense that specific optimizations matter, right? They're going to reduce the computation time even by a year for a 10-year problem. It's going to matter, right? And maybe it's so specific to the particular thing, oh well, it's important for that thing, and that thing is important, right? So high performance computing, by the way, is super interesting because each thing, each problem in its own self is full of complexity. And it's going to come up with solutions that people write papers on and dot, dot, dot. Cool. Anything else? I think I'm done talking for today. But I'm happy to answer questions if there are any. Okay, cool. Next time, more variations on this. Yeah, one question before we all go.
Moore's law is dead. Is it dead in like the single core performance, or is it dead in multi-core performance as well?
Well, no, it's never going to be dead in the multi-core performance. But remember what Moore's law is, okay? Moore's law is saying that on a single chip, we can double the number of devices, right? It's not saying that, well, can you put 50 chips in a system? Yeah, we're going to be able to put 50 chips at the same cost. Okay, so yeah, from a multi-chip system, no, it's not dead yet. And by the way, some would argue that it's not dead from a single chip system either.
The entire lecture we were talking about modifying the way we represent the data, but to optimize performance. But something that I was thinking of is, so for the not edge case, because it's pretty common, but say we have a structure where 10% of it is multiple orders of magnitude larger than the rest of it. I mean, as long as we have heuristic
Testing, testing, testing.